Here we will talk about the Helmholtz uh, Vortex theorem. Uh, this is like the Kelvin's theorem that we talked about rate change of the circulation. Here we are talking the rate change of vorticity. So the Helmholtz Vortex theorem basically deals with the rate change of vorticity. In other words, this is what we are trying to find. So to do that, we're going to start first with the expression of velocity, the total expression for the velocity, total derivative of the velocity with respect to time. We showed that that was equal to partial of t. And we did this in the derivation equation of motion, if you would remember. So we showed that this was actually equal to this, right? Curl of v. And remember, the curl of v is the derivative respect to this, and this was omega, right? And so if we assume that your density is constant and that it's possible to express your body force in the following form, then the whole expression becomes as following. Okay, so now what we could do is we can take this equation and we can take on both sides, right? We take on both sides and we will take the cross product, okay? The cross product of this on both sides of the gradient. And let's see what happens. So if I did that, the first expression becomes the partial of time of the gradient respect to the curl of v plus the gradient of v squared over 2 minus u plus p over rho minus the gradient times the velocity times this all is equal to velocity times the vorticity. Okay, and note that the whole thing here will be 0, and it's going to be 0 because the gradient, taking the cross product of the gradient times a scalar will actually give you 0. Okay, that's by definition. So this is true because f is a scalar. Okay, so now note that this is omega, right? So if I did that, now my new expression becomes omega partial of t minus v cross v times this is equal to 0. Okay, so let's do a couple more expansions and see what happens. So let's work with this term. Let's expand this term. So you can show that you can apply some properties of these operators, and you can show this. I'm just going to simplify it. So this is the same as the dot product of the gradient times the circulation times vorticity times the velocity minus v dot the gradient of the vorticity plus vorticity dot the gradient of V minus V dot this times vorticity. Okay? Now, the couple of things you have to know. First of all, this particular term will be zero because it's incompressible flow. It's double S. Okay? Then also we know that this particular term will be zero because the divergence of the vorticity, we said that equal to zero. Okay, so you're basically, you're only left with these two terms. So let's keep expanding and simplifying, and let's see what we get. So now you have partial of omega respect to time plus v dot this omega minus omega dot v is equal to zero. And note that this is the total derivative of circulation respect to time. Okay, so minus vorticity dot this dot velocity is equal to zero. So this is the expression that we are really looking for, right? There are a couple of simplifications we could do of this equation that are very neat. First of all, we can say, number one, we can show that this term, okay, let's write down, this is actually equal to gradient times the velocity. Okay, so that's what this is equal to. And what we can show is a couple of things. Number one, this expression is going to equal to zero when number one, the obvious reason, if there's no vorticity, right? This happens when the fluid is irrotational. And stays irrotational. Okay, now there's other condition in which what happens is the second item, let's write it on the next page. Second item would be when the vorticity is perpendicular to your stream velocity. Okay, when that happens, then this expression, the gradient of this times the velocity, actually gives you zero. And this is true especially for two-dimensional flow, right? For two-dimensional flow, this will be true. So as an example, to understand this, it says that the gradient of this is in the z, it is in this direction, and your velocity vector is in u I plus vj. Okay, this comes from the fact that since I'm working in two dimensions, this can be a function of x and y, and v can be a function of x and y as well. Okay, so if I take now the dot product of the gradient, I get this is equal to z partial respect to z. Okay, so now if I take the vorticity gradient times the velocity, I get partial of u respect to z plus partial of v respect to z, and you can see this gives you zero, right? Because this is not a function of z itself. It's a two-dimensional flow. So this can happen. So those are the two conditions for which that happens. And what basically you are trying to say when this happens, when this is actually equal to zero under those conditions, you're saying that the vorticity of a lump of fluid stays constant. It's going to stay constant as the fluid flows. Okay, this is what he's really trying to tell you. Okay, one more comment before we move on. This theorem only applies to, this theorem is not true if the fluid is incompressible. Okay, so Helmholtz theorem is not true if the fluid is compressible. Okay. Now the theorem the theorem can be simplified in three theorems. This is the first theorem, second theorem, and this third theorem. The first theorem, it says that the strength of the vortex filament is constant along its length. The second one says the vortex filament cannot end in a fluid. It might extend to the boundaries of the fluid in a form of a closed path. And the third one, it says, in absence of external rotational forces, a fluid the fluid that's initially rotational remains irrotational. So to better understand how this works, let's understand what each one of these theorems works, but that's very important as we move along, okay? So the first thing you have to keep in mind, so let's understand what does theorem 1 and 3 mean. Okay, so to understand this, consider you have a body of fluid, okay, and it's moving along a flow. Okay, and then you have here the normal to this vector is n. Okay, and this is actually coming from a full flow. Okay, so here you have the unit vector n. It's going in the direction of the flow. So this is n. You can kind of see this, right? I may change this. So it's going inwards. Then let's call this phase 1. Let's call this end segment 2. Let's call this C. And this is the vortex tube. Okay, so you have a vortex tube. Remember vortex tube, right? You got vortices that are going all the way along here. Let me see if I can draw that. Okay, vortices, this is all full of vortices, 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 vortices. You have another vortex, it's along this tube, right? This is what it's doing. You got vortex, 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 all full of vortices. It's a vortex tube, right? So, so first of all, to understand what's really going on here, you have to understand that 1 plus C plus 2, they form a closed surface. Right? You can see this. If I got this, I got the tube. I'm going to call this surface area of the tube C and the end surface area 2. So this is all enclosed area. So if that is true, that means that the net outflow of velocity or vorticity from C1 and 2 has to be 0, right? In other words, there is no flux of vorticity across C in any single point parallel to omega. So as this is moving in this direction and this is rotating in this direction, right? So this is having a rotation. So what I am trying to tell you here is that there's no vorticity that's going outside. So no vorticity is actually going in this direction, and it's going in this direction. It's always staying in this direction right here. So let's write that down. Okay, so if you want to pause the video for a moment and take notes here, you may do so. I'm just summarizing what I wrote in the previous chart. So as a consequence, I can say that the integral of this dot n ds plus this is surface area, integral of this dot n ds, this is over surface area 1, surface area 2, is going to equal to the circulation gamma, right? The circulation around the tube. So in other words, then what we have done is we have basically said, and we know this, right? Um, that your circulation, we can define your circulation as the strength of the vortex tube. Kind of makes sense, right? For a weaker, for a circulation, for a vorticity, the vorticity that's small, you're going to have a smaller circulation. You want a bigger circulation, then you need to have more vorticity. Okay. So there's another interesting aspect of this is the Kelvins theorem. How do we combine Kelvin's theorem, the application of Kelvin's theorem, to Helmholtz second theorem? Okay. So what we have is we have your vortex tube. Okay, we got your vortex tube. And remember, this is vortex tube. So you got all these vortex lines coming here. And so this is the vortex tube at time, let's say t. Okay, this right here. Not this end, just the tube itself is at time t. So what I can do is I can define a fluid loop at the time t on the surface area of this tube. So I could take this and I can say I'm going to define this loop. Okay, let's call this loop C. So this is a fluid loop defined at time t on the surface of the tube. Okay, and then what we know is enclosed tube, right? So the circulation around the enclosed tube, C is going to be 0 because this cross, there is no, there's the dot product, the cross product of your rotation vector times your ds will be 0 if it doesn't exist. Okay, in this small loop right here, it's going to end up to be 0. And what is also important to understand here now, well, I can generalize this, and I'm going to say that your total circulation is equal to 0, and it's going to remain 0 as the fluid loop convects with the flow along the body. So there, and the pressure viscous, just remember, this is all based on the fact that your body forces, pressure loads, and your viscous torque are absent. Okay, these are going to be 0. That's the only reason I can assume this. And also, we can think that it doesn't matter how many loops I can draw around this tube, they're always going to convect with the fluid, with the material. Okay, that's what it really means. And it doesn't matter how many times I do this, my small loops are going to be 0. And if they can be 0, that means that my tube will convect with the fluid material. Okay. So let's understand what are some applications of this, some direct applications of this. So first of all, before we do the applications, let's see some kinematic conditions. For Helmholtz second theorem. Okay, so we define and we know that this, okay, I just told you this. This has to be 0, right? This is for the fluid line. Okay, if this is 0, then your total expression is actually equal to this dot B. Okay, and this will be true only when vortex lines convect with the fluid lines, and all other torques are 0. Okay, we already said that. So this is the condition for which Helmholtz second theorem should be applied. And some of the applications are very interesting. As for an example, consider the case of a submarine, right? So if I have a submarine, I have a flow that's passing the submarine, and you can see that the density, and I assume that the density of my ocean at a specific point will be constant. Then I can show that my vorticity, or my vorticity will be 0 everywhere. In other words, I can say that my rate of my vorticity changing with time is also 0. So what do I mean by that? I mean that if I take the gradient of the velocity, that's going to be 0, meaning that it's possible to write the velocity as maybe some function gradient times a scalar that will also be 0. This will imply that the fluid is irrotational, that the flow is irrotational. Okay. And where is this irrotational? It's rotational everywhere around my submarine. Irrotational. And if that's the case, then I can say that the enclosed integral of all my body forces, okay, will also be 0. So I'm saying all my pressure loads is also 0. Okay, in that case, if that was the case, then my conclusion is that my total change of vorticity is actually going to be 0 across my submarine. Let's consider a second case. Let's consider a case of a fan blade, right? A jet engine in which you have an air that's flowing. So this is uh, aircraft aircraft engine flow, or let's call it bypass. Okay, so you have air that's flowing in this direction, a stream velocity, and assume that's coming constant. And this is a solid body rotation right here, right? And then I want to know what happens to the flow, let's say, this cross section. If I did that, you can see from the top, this is my fan blade wave, which is actually rotating, right? But what is true is what happens between one fan and the other one, right? One of this blade and the other blade of my fan, what happens inside this, I can show that my vorticity is equal to 0. Okay, and that's actually a direct consequence of Helmholtz Helmholtz theorem. Okay, so another case that you can think that's very actually, I would say, the most wide application to this of this theorem can be seen in wind tunnel testing. Okay, so wind tunnel contractions. So consider the following case. So you have a case in which you have a wind tunnel. Okay, the wind tunnel, usually the purpose of wind tunnel, you have a reduction, right? Reduction in area. So you basically, in this location here, I have an area A1. Here I have an area A2. Okay. And let's call this the surface area A1 and A2. So what I'm going to do is I have a vortex, I have a vorticity that's being created here, and I'm going to call that vorticity 1. Now I am going to have, as a consequence of that reduction, I'm going to have another vorticity, that this vorticity is going to be reduced, and I'm going to have a omega 2. And the question would be, what is the value of that omega 2 in this test section? This is my test section, okay? And in this this right here is my test section. This is what I want to test it. And my area there in my test section, let's call this S2, A2 of T. Okay, so I have a streamwise vorticity that's going through the chamber here, and we're going to have some vortex tubes that are lined up with the flow, right? I got my flow coming in this direction. So they're actually going perpendicular. They're 90 degrees here at every single time in this particular location. And so in order to understand this, let's go ahead and define a parameter. You're going to call this the test area section parameter, and it's called the reduction area, because you say A1S divided by A2S. To better understand what's happening, this is the area reduction parameter. Okay. So I want to point out here that my tubes that are actually they're going, okay, all this vortex tubes here, they are at 90 degrees with my flow. Okay, my flow is going in this direction, they're completely 90 degrees. All my vortex tube is doing is becoming smaller. It's still there 90 degrees, it becomes smaller, and my flow is going there. So the question would be, how much does that affect my vorticity there then? And so that's this right here, this 2. It is the goal of these theorems will be, we want to estimate the streamwise vorticity in the test section. Okay, so again, this is what we are trying to do. So what are some of the assumptions that apply? So the assumptions is going to be that each one of my three theorems apply, right? So assumptions. It says that the Helmholtz third theorem applies. What does the theorem state? So remember, it says that in the absence of rotational external forces, the fluid that is initially irrotational remains irrotational. So the first assumption is the fluid is irrotational all across as I move along, okay? And then the second, Helmholtz's second theorem also applies, right? What does the second theorem say? A vortex filament cannot end in a fluid. It must extend to the boundary condition and form a closed loop. And we know that, right? There has to be an enclosed. So that's why I enclosed this area and this area. So this is enclosed area. So second theorem also applies. And the third assumption is going to be that my first theorem also applies. What does my first theorem state? My first theorem says that my vortex tube is not going to change with time. Okay. So this means, so all these theorems, let's assume that they apply, and let's see what happens now. So I am going to start working with the equation of continuity. Okay. So the equation of continuity equation states that A2 L2 is going to equal to A2 A1 L1. Okay, this is the area of the tube. Okay, in other words, what I'm showing here is that area 2 over area 1 is going to give me L1 over L2. That's actually going to give me R. We know that omega 2 then in this case, we can say is going to equal to this times RC. What is RC? RC can be defined as the inverse of R. And so this is very powerful. It's very nice to understand this because that means for a rectangular shaped case, I have R is equal to area 1 over area 2. That means my RC would be area 2 over area 1. So this is how much this is actually changing. If let's say I had a circular cross section is actually given by the square root of A1 divided by A2. Okay, so in that case, your RC will be the square root of A2 over A1. So this is how this vorticity is going to actually change in this problem, and you can find that you can find that answer. So I want to know how much is this, right? How much is this omega? All I have to do is find this ratio for which this is changing. You can see this is going to be smaller value, right? So that means the vorticity that's happening in this example, right, where I go with a larger area to a smaller area, that means that this has a larger area to a smaller area. This ratio is bigger than 1, and the ratio will be less than 1. So I'm saying that what happens at sigma, the vorticity, magnitude of vorticity at 2 will be smaller than the vorticity at 1. So this is where it really happens. So there is another interesting case, another application to this, and it's the case of a curved channel. What happens in a curved channel? So in a curved channel, what happens is, so another example, the application of this. So if I had a case of a curved channel, so let's really understand what's going to happen here. So here you have a vorticity, okay? This is the fluid line. This is the direction that is flowing. You got a vorticity that are rotating in this direction now. We call this BB, AA. And now you have a channel that's actually at an angle alpha. It's a constant angle alpha. These are straight lines. So your flow is coming here and then it's doing this, right? Your flow is just staying constant lines parallel to this. This is your flow, this is your flow, this is your flow. Your vortex tube comes here, and now this is A prime. You can see that what happened here was your vortex tube actually rotated now at alpha, right? The question will be, well, not the vortex tube, your fluid line rotated. Now the question is, what's going to happen with the vortex tube? So because there's no vorticity out of the paper, well, the tendency you might think, oh, this is really going to happen. This is really going to do like this. Well, it's not correct. It's going to try to oppose what it's going to try to do is, it's going to try to oppose the fluid lines, okay? Since it goes the wrong direction, it goes here, and the vorticity wants to kind of stay in the same direction. And actually, what the vorticity then ends up doing is, uh, so what the vorticity really ends up doing is, it ends up actually rotating, trying to stay in the same direction, okay? Because has no reason why to move, okay? So this stays at the angle alpha, although this is at angle alpha. Okay, the direction of vorticity after the corner is, as you can see here, since there is no vorticity out of the board, and since there is assumption there's no other torques, no body forces, no pressures, it's going to actually try to rotate in the up. It's going to try to stay in the same direction, or think about it according to flow, it's going to rotate in the opposite direction. Okay, your fluid rotated in this direction, and this rotated in the opposite direction if you look at it in sense of that this has to be perpendicular. So now my vorticity is no longer perpendicular to my flow. And the reason behind it's not any perpendicular is because of Helmholtz uh, three vortex theorems. Okay, so this concludes the discussion on Helmholtz three vortex theorems, and next we will do some examples.